Okay, welcome back everyone for the last session of today. For the last talk, we have Professor R. Vijayraghavan from TIFR Mumbai telling us about some experimental aspects of quantum information. In his 2-lecture series, the first talk is an introduction to quantum computing hardware. Over to you, Vijay.
Thank you for the introduction and thanks to the organizers for inviting me here. I realize this is going to be a very different talk, not too many equations. But in tomorrow's lecture, after what we covered today, where I'm going to just give you the basics of the systems where you actually can do these kind of experiments, right? Systems which behave quantum mechanically, these are real systems, these are not existing in some abstract space. How do you actually build those systems? How are they controlled? So the idea here is to give an exposure to that with a very particular focus to one technology, which is the superconducting circuit-based technology, which is what I do. And but I will mention some of the others, and in tomorrow's lecture, I may go into a little bit more detail of some of the other hardware approaches. But I will also try to talk about some aspects of the experimental developments which emerge from some important theory result, and also some challenges in the experimental progress which may rely on some important theoretical developments. So that it sort of connects to the broad area, what are the things which one can do, both from the experimental side and theory side. It'll just be a very brief flavor. I won't have time to go into very comprehensive details on that. So that's the plan, but at the end of the lecture today, if there are some specific topics of request, I can take that and try to include it in my lecture tomorrow. Okay, so you've already had lots of basic lectures, and I think Professor Radhakrishnan has given an overview on quantum information in general, but the most basic concepts I will briefly cover in a few slides and then go on to the hardware aspects. We need a quantum two-level system, right? A physical system which can represent or can be modeled as a quantum two-level system, and that is what a quantum bit or a qubit is. And when thought in terms of storage of information, there is a very big difference that because these are quantum states, we can create superpositions of these states as well. This is something which is, of course, not possible with classical bits. So physical system, which is a quantum two-level system, can, apart from being prepared in its eigenstates 0 and 1, can also be prepared in this general superposition. And this kind of parameterization allows you to view this state on the surface of a sphere with the north and the south poles representing the eigenstates and all the other points representing some superposition. So you can see there are many, many possibilities, and you can graphically represent them in this block sphere representation. So that's the first main idea, that you have this ability now. You have a system which can do this, because we need to see whether this is of any use. And one question which often comes up and it's often misunderstood, and I like to sort of clarify that at the beginning, is this idea that there are so many different superposition states which can be encoded seems to suggest that somehow one qubit can store much more information than one bit, right? Just to give you an example, I could choose 26 different points on this sphere which are distinct and call them as the alphabets of my English letter, right? So it looks like just with one qubit, I can actually store all the alphabets. In fact, I can go further. There are an infinite number of points on this sphere. All of them are distinct. So it seems to suggest that somehow there's an infinite number of states I can store. But of course, that is not true, because of the second sort of odd aspect of these such quantum systems, that when you measure them, when you create a superposition and you measure them, then you actually still only get one bit of information. The answer is either 0 or 1, and the probability of getting that, so it makes matters worse, that it's not even a deterministic answer. When you store something, you would like to recover it deterministically. The answer is random. It depends on the coefficients of 0 and 1 in the superposition. And after the measurement, as textbook quantum mechanics tells you, the measurement, the system changes or collapses into the eigenstate corresponding to the eigenvalue you measured in your in your experiment, right? So it's important to remember that you have infinite possibilities to encode, but the recovery is still only 1 bit. Okay, so it's not a better memory in this sense. You cannot store more information in this sense, but you can do some other things because of this possibilities, right? And this is where we sort of now extend this idea to more than 1 bit. You extend to the idea of having n bits, and if you start with the classical bits, and you say I have a register of n bits, then there are 2 to the n possible combinations you can make with those n bits. But at any one point, that system can be only in one of those 2 to the n configurations, right? So that's always going to be the case for a classical situation. But when you now extend the idea from what we discussed in the previous slide, is that if we have an n qubit system, there are 2 to the n possible eigenstates, but now you can put the system which is in a superposition of all of those 2 to the n eigenstates. That is not possible in the case of the classical register. And it is this vast size of 2 to the n which sort of starts to indicate why quantum information processing may be more powerful. Right? But this is still not the end of the story. The thing is that a quantum algorithm now plays around in this gigantic phase space, which is exponentially growing with the number of qubits you have. And it still needs to do something more because of the caveat that at the end of whatever you do with these n qubits, you're only going to recover n bits of information. You're going to get a string of zeros and ones of size n. So all the magic needs to happen here, where you're playing around in a much bigger phase space, which we now call the Hilbert space here, as opposed to a classical computer with n bits. And because these are quantum states, they are wave functions, these states can interfere, and the algorithm needs to exploit these properties to evolve the combined state of this n qubit system towards something which resembles the answer to the problem you're trying to solve. And this is non-trivial. There are only a handful of very well-known algorithms which sort of very clearly demonstrate why you do much better than the best classical algorithm. There are many applications based on those algorithms, but to invent a new algorithm is non-trivial. Because how the ability of the superposition, and then when you extend the idea that with the multi-qubit system, a class of those superposition states are also entangled states, how that benefits a particular problem is not, there's no formula for that, to the best of my knowledge, that I take some classical problem and I run it through some operation and out comes a quantum algorithm which is better, right? And it's also true that not all problems will benefit from using a quantum computer. So there is a very sort of general hand-waving argument that problems where you have to explore many paths simultaneously can probably do better on a quantum algorithm because those paths can be explored in parallel because of the superposition nature. So essentially what happens is that the algorithm processes every path corresponding to each of the states which are in the superposition, and if it's done correctly, at the end of the day, you will have only those weights surviving which correspond to the final answer. So this is hard, but there are sufficient number of algorithms and sufficient sort of shown applications which warrants the building of the machine of this type. So back in the 90s, Peter Shor invented the Shor's algorithm, which showed that finding prime factors of large integers, which is a very complicated problem and is the basis of how data is encrypted in this RSA encryption scheme, can actually be done in polynomial time using a quantum algorithm. Then you had the Grover's search algorithm, which showed a square root of n improvement. And then if you actually even go before that, the original motivation of building a system composed of objects which show quantum mechanical properties was actually to study quantum mechanics itself. This aspect that the phase space grows as 2 to the n is also the reason why solving quantum mechanical equations in a brute force way on a classical computer is very, very hard. You just run out of memory and processing power very soon. You can solve a small atom or a molecule, but by the time it comes to any reasonable size, you just cannot represent it. So of course, people found approximate methods to do that. But if you really want to study it in a brute force fashion without many approximations, you need a system which can represent that faithfully, and for the amount of classical resources you need blows up. But for a quantum computer, you only need to worry about the n. So if it is a quantum system which can be represented by n qubits, you only need n qubits, because that n qubits automatically gives you to the n-sized Hilbert space. So this is sort of the broad area of what is called as quantum simulation, which is often traced back to Feynman's original suggestion that this would be a nice thing to build. So this is sort of the start and why people started worrying about actually building systems where you can put things in superposition and create entanglement. And it should be something which is relatively easy to use. The main problem is that any such physical system people have been playing around with, they are inherently unstable. What do I mean by that? It's this very simple idea that when I put some system in the excited states, typically you have some system, maybe here as an example, you have an atom, maybe it has electronic states, and I choose 2 of those electronic states to represent my quantum bit. If I put the system in the excited state, it wants to come down to the ground state over some characteristic time scale, which depends on the property of the system you're looking at, right? If you think about this from the point of view of memory, that's horrible, right? I just finished my talk in my room, and I come to the lecture hall, and all my bits are 0, and I don't have any talk to present. That's terrible, right? Our memories can last for years without getting corrupted. So classical memory is extremely robust and stable. But quantum bits, the ones we have been playing around with till now, they are not. These time scales can be nanoseconds, milliseconds, or a few seconds. If you tell somebody in the quantum computing world that your system can be coherent for a second, they will be very, very happy. But I'm sure you won't be happy if your data only lasts for 1 second, right? So this is a big problem, and this process called relaxation is one of the things. And in borrowing from the NMR literature, this number T1 time tells you the time scale over which these relaxation processes happen. Now, in addition to this, we also have these superposition states. So if I now, just wanted to add that these relaxation processes are typically connected with some dissipative process in the system. We'll come back to that when I talk about a specific example. So we also have these superposition states we have to worry about. Now this superposition state, which is an equal superposition of 0 and 1, because it's right in the middle, it's on the equator here. Now this also will suffer from this process. It will come back to the ground state over the same characteristic time scale. But it can also undergo another process, which is that when you write down a superposition, it actually matters whether this arrow is pointing towards like out of the board or on the side. There's like, again, an infinite number of possibilities. So this angle is also one of the things which characterize that particular superposition state. So this state can actually, over a characteristic time scale, can get completely randomized due to a process which is often called dephasing. So not only is that your state is wanting to go back to the ground state, but it can actually also start wandering randomly along the other axis, and that is also bad because this is the state you stored. And then you may want to change this state to something else as your algorithm proceeds, but the environmental processes of relaxation and dephasing are basically taking that state and turning it into some random state over a characteristic time scale. What this means is that on this time scale, your original quantum state is completely gone, right? And that is bad because your algorithm started with some well-defined quantum state and it wants to evolve it in some deterministic fashion. You would like that to be preserved. And this is a problem, and currently all quantum hardware which is available are limited by these processes. So you try to make these as long as possible, and you try to do your computation in a time which is much shorter than these time scales so that you can hope to trust. Remember, these are probabilistic process, right? You can still have a decay event in an infinitesimally small amount of time, but you can trust your calculation more and more if it is short compared to the time scale shown here. As I mentioned earlier, these time scales can quite vary. For one of the most popular systems, this time scale, which is the superconducting circuit-based systems, this time scale is of the order of 100 to a few hundred microseconds. In ion and atomic systems, it can be milliseconds to a second. But what actually matters is not just this time scale, but this time scale when compared to the time it takes to do an elementary operation. Okay, that's the number which is important. So we'll come to that in just a second. If your system can survive for a long time, but to change the state is also very, very slow, then you can't do many useful operations before it starts to get scrambled. So, and these dephasing processes are often connected with frequency fluctuations. And what I mean by that is that it's the energy gap between these two levels. They can fluctuate in time. That sort of is a representative process which can give you this kind of a noise. So does this mean that all hope is lost? And it did feel like that at one point of time when people were thinking about these systems. But then there was a major theoretical development, something called quantum error correction. I won't have time to go into this at all in these lectures, maybe in the next lecture if there's some interest. And this essentially said is that you don't need to make so we often call these as the error rates, like what is the error rate of a state changing into something else. You don't have to make them zero, you just have to make them small enough that by combining several such systems, you can encode data in a very special way, which is protected against these kind of processes. Okay. So what you do is you now, if you want one good qubit, you need many not so good qubits, and you encode the state of one qubit amongst those multiple qubits. And then the idea is that the individual qubits can undergo these kind of processes, but by doing very careful measurements, so here again the projection of quantum states plays a big role, and entanglement of quantum states plays a big role. You can actually see that there has an error that has happened without revealing the underlying information that is stored. And because that is fundamentally not possible, right? If you have a superposition state, and if you measured it in any way, it's going to collapse. That's not what you want to do. So that's sort of one of the weird aspects of error correction. You want to look at the state, but you don't want to get the information. So you look at something else, which is the error. So you need to create a big enough Hilbert space that there is space for these states to exist and for the error syndromes to reveal themselves without revealing the information about the state. So this was the solution. It is on very, very firm theoretical footing. There is no doubt that it works. By the way, error correction is also very common in everyday communication, in classical communication as well, because when things are transmitted, zeros can become ones and ones can become zeros. And this is done routinely. Like all your Wi-Fi connections and everything, they use internet, they use error correction. In fact, the reason the speed of a Wi-Fi link becomes slow as you go far away from the router and the signal becomes weak is because of that. I don't know if you ever thought about it, that look, the speed of light is really not changing. Why is the speed of data transmission changing if I'm just a few meters away? Right? It shouldn't make such a big difference. It's because the system has to work hard to send more information. Sorry, did something happen? Somebody error corrected it in between. Okay. Yeah. Please. That's what we do today. But that'll only take you so far. Yeah. When people have come up with metrics, if you can make these numbers very, very large. So the real question is that what are the useful calculations and how long they are in terms of the number of operations, and whether you can make your time scale much, much longer than that. So there are estimates, but they are typically 4 or 5 orders of magnitude better error rates than what one hopes to achieve in the near future. So it may take much longer. So that's why, of course, the people have done algorithms, people have shown results, but by executing them only on time scales which are much shorter. There are some techniques. IBM has been promoting one particular technique called error mitigation as opposed to error correction, where for some class of problems, you can actually study the answer as a function of the noise. So there is some background noise which is always there. You then add sort of intentional noise to it, and then you see how your answer deteriorates. And then you sort of do a backward extrapolation to guess or estimate what the answer would have been if there was no noise. And in some cases it works, but it's not really a general solution for all kinds of problems.
Random. How would you be able to look at the noise and then figure out?
Well, you can look at the errors in your system and you can model them. So they are random, but it's like saying that I can always create a random signal. It's like, as I mean, a very naive example would be a simple Gaussian noise is only characterized by its mean and standard deviation, right? So if a particular quantum computer has a noise which is characterized by a certain amount of standard deviation, I'll now add a same type of Gaussian noise in this case to make the overall noise standard deviation larger and larger, look at how the answer changes, and then sort of do a reverse extrapolation. I'm giving a very simplistic picture here, but there are papers which have shown that this works for some kinds of calculations. Yeah, so this is a very important milestone. Many experiments have shown that the basic idea works, that you can actually do this, but it's not at a stage where it is really useful in the sense that there is no quantum computer where you only have error-corrected qubits and you can do any operations with them. It's getting there, but we are still, so this is a big milestone, but there are, as I said, there are other techniques which people are using in the meantime to sort of get something useful out of these error-prone machines we have today. Okay. Yeah. Yeah.
That would also
yeah. So the way so what Sandip is referring to is the fact that the way I've explained it right now, again in a very simple fashion, is only about the storage aspect. Like, how can I store a quantum state in this error-corrected system and preserve it for a very long time? That's not just enough for a quantum computer. It needs to be able to do those operations. So while you are now carrying out those operations, and you will see in a little bit what those operations are, you also have to do that without losing your error correction. So that is another layer of complexity, but there are, again, solid theoretical ideas on how to do it. Often the challenges have been, and in fact, this is maybe a good example to mention, is that often those prescriptions are not easily translatable to a particular hardware, in the sense that there may be much more overhead for a particular hardware to implement that, because at the end of the day, the error correction is also like a small algorithm. It's like something which is running on top of your underlying system, and if that is too long itself, then it doesn't help. So it will actually introduce more errors than it corrects. So you have to be able to do that properly as well. So that's another layer which we have to figure out. But again, nothing fundamental says that this is not possible. So people are working hard, and there are various ideas on how to do this. Okay. So keeping these ideas in mind, if we now try to define what this generic quantum processor is, it's really just a network of qubits. An example shown here is a linear array. So the blue circles are representing these quantum two-level systems, and these red connections represent some kind of interaction, and I will emphasize that in just a little bit. And here it's sort of showing nearest neighbor interaction between these collection of spins. You can have it like that, or you can have a square grid where now each qubit has more connections. The reason this connection is important will just clear in a bit. So after building something like this, you need the ability to do something called local qubit operations. What that means is that I should be able to access any qubit in this network and change its state to whatever I would like. Okay, that is what is called as a local qubit operation. You also need these other class of operations, at the very least, called entangling operations. Now, these necessarily involve more than one qubit, right? The way to think about them is that if we go back to our Boolean logic and electronics from high school and early college days, you have logic gates like NOT, which take a 0 and turn it into a 1, or take a 1 and turn it into a 0. These are single bit operations, right? The single qubit local operations are of that nature. But most useful ones are the ones which involve more than one bit. So if you have something like an AND gate, where you have two inputs and the output depends on the state of both of the two inputs. So here you need, in order to create an entanglement, and I will give you some more details later on, you need the qubits to have some kind of physical interaction with other qubits. Ideally, you would like them to be more densely, but theoretically it has been shown that nearest neighbor is sufficient, but having an extended connectivity is useful, okay? This is an example of nearest neighbor connections. For example, this qubit here doesn't directly interact with the qubit which is sort of 2 rows over. But if my algorithm wanted to entangle these two qubits, then I cannot do it directly, I have to do it via this intermediary. So it adds an extra step. So that's the price you pay. In principle, it is not a problem. What people have shown is that any unitary operation on this n qubit system can be broken down into pieces which are composed of local 2 qubit operations and entangling operations with only nearest neighbor. But the number of such steps will be much larger if the connectivity is limited. It will be smaller if the connectivity is extended. What do I mean by an extended connectivity? It's like if I could draw a red line from this all the way to that qubit. Ideally, the most ideal solution, what is called all-to-all coupling, where each qubit is coupled to every other qubit. Right? But you can also imagine that you might have heard that useful quantum computers need millions of qubits. It's almost impossible to imagine a million qubit network where every qubit is interacting with every other qubit, right? It's physically impossible to imagine how you can do that, but there are some ideas on at least improving it beyond nearest neighbor as well. And this trade-off will again come down to coherence. If coherence was infinite, then you don't worry about it. You just pay a little bit of overhead in doing some more steps. But if coherence is finite, then you will struggle to create entanglement between qubits which are far off in a network because you have to do many, many steps. And during that time period, you will decay. Yeah.
To make any general state?
So so even like something like a linear thing would work, but this is sort of the simplest nearest neighbor connectivity you can have. But you can have even weaker ones. So for example, one of the, in fact, I think I have it here. Yeah, here. So this is the layout of one of IBM's quantum computer qubits system, which is 128 qubits, I think. So the way to look at it carefully is that it's literally a linear chain, like follow my mouse pointer here. It's a linear chain with a few cross streets, right? And that's sort of enough, which means that there is a path to go from here to here, which doesn't involve traversing the entire chain like that, but you can take a few shortcuts. So it's now a trade-off on how many such steps you want. So otherwise, this is also sufficient, but it will be extremely inefficient to do something like that.
And each one of those these little lines should be thought of as a unitary which only entangles those 2 qubits. Right?
Yeah, correct? So the presence of that line allows the possibility of directly entangling those 2 particular qubits. Yeah. So again, to go back, local qubit operation, entangling operations between pairs of qubit, then local measurements, because at the end you would like to measure each of these qubits to find out whether it is a 0 or a 1. And what you're fighting is the fact that you have limited time to do this without error correction, and also to do this on scale. Now, this again comes back to the point when I was talking about this 2 to the n, right? If you only had 5 qubits, it's a quantum computer, yes, but it's not a very useful quantum computer. Because at the level of 5 qubits or 10 qubits, I can actually write down the equations on a regular computer, and I don't run into this problem of not having sufficient resources, and I can calculate exactly how that quantum computer would evolve. And it will do that without any problem of coherence or anything. It will give you perfect results. Whereas any 5-qubit quantum computer actually built using quantum objects anywhere in the world today will make errors. Okay? So, it's a path along building larger systems, but quantum computers become useful only when that n is large. When that 2 to the n becomes large enough that it is now handling problems which just you cannot even imagine representing them on conventional computers. So this break-even point is approximately 50 to 100. And a few years back when Google made a big announcement about demonstrating quantum supremacy, that was around 53 qubits. And it's basically around this number where brute force representation of that system on the world's most powerful supercomputer becomes quite hard. And once you, I think, cross 100, it's almost impossible. There are some approximations you can do to find things out, and that's why you often keep getting, so every time somebody makes a claim, some theorists go back and do some calculation. No, you can simplify this and you can actually run it on a much less powerful classical computer. So this is an ongoing game, but at some point, 2 to the n will just become too large, right? And a common number which is thrown out is at n equals 300, 2 to the 300 is more than the number of atoms in the visible universe. So it's an enormous number, but 300 qubits is nothing if you think in terms of the number of bits we have on our phone, right? We have 4 GB RAM, that's like 4 into 8 billion bits, right? And we are talking about only 300 qubits, but it's the access to the 2 to the 300 sized Hilbert space which makes it powerful. So to be able to do all of this becomes more and more challenging as you make the system larger and larger. Connectivity, how to address this, how to pack all of this in some reasonable size, all the hardware, and you will now get a flavor for what are those things which one needs to make such systems. Yeah. Yeah.
There was a discussion at lunch. Let me ask you. Yes. For one logical qubit, given today's state of art, how many physical qubits do you roughly need? Sorry.
Yeah, so there's actually not a single answer to this. There are error correction codes which say that the simplest one, which was probably the first one invented, was Shor's 9-qubit code. He first showed the Shor's 3-qubit code, which only could correct a certain class of errors, a very specific kind of error. And then he showed that by combining 2 such things, you can actually correct all errors. So 9 qubits. So at that time, it was felt that 9 qubits is the minimum you need. Then I think there was a 7-qubit code, and I think there's also a 5-qubit code as well. The problem is that most of those codes are still not, it's not possible to implement them efficiently in today's quantum computers because they require a lot of entangling operations across the entire network of 7 or 8 qubits. I've actually not checked what is the best demonstration of a 7-qubit, I think it's called a Steen code or the 9-qubit Shor code, but they are actually not so easy to demonstrate even if you have, we have quantum computers with 100,000 qubits today, but it's not so easy to implement that particular 9-qubit. You can say that it's a 9-qubit algorithm because it requires a lot of operations between distant qubits that makes the overhead large enough with today's error rates that it doesn't work properly. So that's the reason there are other approaches which people are using, and one of them, the most popular one, is something called a surface code. And that surface code was designed keeping in mind that a typical chip-type quantum computer will have some 2-dimensional array of qubits with some nearest neighbor connectivity. So it relies on that, and there, the number of qubits, physical qubits per logical qubit is not a fixed number. There is a threshold, your errors have to be small enough. But if you are just above that threshold, you're going to need an enormous number of qubits. So it's sort of an extendable fabric. Depending on how good your qubits are, that will determine the size of the fabric you're going to need. So it's called a fabric because it's a 2-dimensional thing. So errors are bad, you're going to need lots of space. If errors are not so bad, you're going to need some minimum number of qubits. And because of the practicalities of the surface code and the realities of the hardware, how the hardwares are built, it looks like that might be the way to go. And people had made some estimates and for saying that, okay, for some 1,000 qubit logical qubits, you may need some millions of physical qubits. And there were some blueprints and all which is created. But again, surface codes have only been demonstrated in small fabrics till now. But it's looking promising. So this answer of how many physical qubits really depends on what code. The simplest ones have very small numbers, but they are hard to implement on today's hardware. And this is actually one of the areas where if theorists and experimentalists work together, maybe it is possible to invent a new code which sort of takes into account the realities of what it takes to build a system like this and the requirements of doing error correction. So surface code kind of emerged, I think, in that way. So now moving on to the actual physical systems which are needed, there are actually quite a few. Some of the earliest experiments were done using individual ions. It makes sense. Sort of quantum mechanics was invented to explain the atomic world. So here, this picture is what it's showing you is two ions trapped in an electromagnetic field in vacuum and fluorescing. And in fact, it's this fluorescence which is what is used to detect the state of those ions. And you're using some electronic states, carefully chosen electronic states, pairs of electronic states which are long-lived. And that depends on the particular species of ion you're using. For a calcium ion, it would be different. For an ytterbium ion, it would be different. And then these individual ions, each ion is a qubit, and you trap them using electromagnetic fields, typically in a linear array. And such a system is called an ion trap-based quantum computer. Similarly, there are neutral atoms which can be trapped in optical fields. That's called a neutral atom quantum computer. There you can actually trap them in 3 dimensions using optical lattices and similar techniques. So that's one which is probably one of the first ones. And back in 2012, the Nobel Prize was given to Dave Wineland for developing the techniques for manipulating individual quantum systems, right? Going back, the founders of quantum mechanics never thought that quantum mechanics can actually apply to a single atom, right? All things we study, our expectation values and everything which we calculate are for ensembles. And in fact, I think Schrödinger himself was very unhappy because when you start applying these ideas to individual quantum systems, then you get these bizarre things like quantum jumps, and they were all very unhappy about this. And so this was sort of the first time where they showed that you can actually control an individual quantum system and control that degree of freedom very precisely. And at the same time, the corresponding techniques for manipulating individual photons and storing and recovering quantum information on that, Serge Haroche got the Nobel Prize. So they both jointly got it in 2012. So these were the earliest sort of systems which are still, yeah. So the question is, what properties of the ion do you need for it to be a 2-level system?
Yeah.
No ion is actually a 2-level system.
Approximately.
So the requirement, in fact, this is true for most qubit systems, and you will see that for the superconducting qubits, is that you need 2 levels which are far away from other levels, right? And typically the way you create transitions between these levels is by using electromagnetic radiation which is resonant with that energy difference. So as long as nothing else is resonant with that same transition, you can localize your quantum state to those two levels.
Okay, thank you.
So that's why not every ion is usable. You have to find the right ion where you have the right, and this is very commonly done. Like even for optical clocks, that's what you do. You find 2 very stable lines because that defines a very stable frequency, and that can be used as a standard for keeping track of time. So it's similar requirements. But for doing quantum computing versus doing atomic clocks, there are some other technological aspects which are important. So that's why the species are often different for that. Okay. So I would call this a microscopic degree of freedom. It's an individual atom or an ion. Right? Another one, which is called quantum dots, is using the degree of freedom of a single electron. But these are not isolated electrons in free space, but these are electrons sort of confined in a two-dimensional electron gas in a semiconductor chip. So this is sort of an artist rendition. These gold things are actually electrodes on a chip, which are applying electromagnetic fields to create an effective puddle here of electron, which behaves like a single electron. And then you apply a magnetic field to split the spin states of the electrons, up spin and down spin, and that creates your two-level system. So here actually you sort of create that by applying the magnetic field, and the amount of magnetic field you apply determines how large that spacing is. And typically it's chosen to be in the microwave frequency regime around 20 to 40 gigahertz to operate this. This is all done on silicon, and it's often said that the processes are compatible with our other silicon fabrication techniques. So, but there are other challenges here on creating interactions between one such electron and the next electron over to the other right near it, and that's one of the limiting factors of this particular technology. And what I'll be focusing the rest of the talk today is making such quantum two-level systems using a superconducting circuit. Right? This here is a film of aluminum on a silicon substrate, and there's this square is about 5 microns by 5 microns in size.
Jay, I have a question. You're talking about fabricating two-level systems. Why only two? Maybe if you have more level systems, maybe you're...
Yeah, so why only two-level systems? It's sort of similar to why only bits in classical computing. There are models of doing quantum calculations in a multi-level system. In fact, you will see that most quantum systems we use are indeed multi-level systems. We approximate them as two-level systems. Sometimes the other levels can be a problem or they can be an advantage. It's really I think for classical hardware, it's much easier to define two robust states, and then everything is sort of just repeating the same thing. So I think that moved on to the quantum picture. And I think there is I'm not aware of like a hard proof there, but I'm sure it exists. You can do quantum computing. People have done experiments using what are called qubits or qubits, which is in general true. But if you show that there is a practical advantage of doing that, I'm sure somebody would build that. It's just that you don't need to go there. It doesn't offer you any fundamental advantage than doing it with two-level systems. But as I said, if there's an easier way to do it because of technological limitations, then absolutely. Yeah. In fact, I think Sandip, one of your students who's at the Albag, he once told me that there is a qubit error correction code, which is a lot more efficient in terms of the number of qubits you need to do a full code. So it's just the size of the Hilbert space kind of argument. So it's a practicality question. So coming back to this, this is a film which is about 5 micron by 5 micron in size. So if you compare that to these two other approaches, this is completely different. Right? These are microscopic degrees of freedom, whereas this is something which is quite big with, I cannot say this is composed of one atom or a few atoms. It's composed of millions of atoms. And this sort of connects to this whole idea of macroscopic systems showing quantum mechanical properties, to Leggett and all the work they did. The trick is that your system could be microscopic, but the degree of freedom you are trying to, which is basically quantized, if you can isolate that and protect it from environmental decoherence, then that will show the correct quantum mechanical behavior. And this is of course now done routinely, but all of these systems are equivalent in terms of their ability to do calculations or process information. And there are many other platforms. You can use photons. You can use the polarization states of photons as a way to encode 0 and 1. And this is actually making a big comeback after some initial results. And the reason is that while photons are very, very coherent, they don't like to interact with each other. And if you cannot make them interact, you cannot do 2-qubit gates, and that's the end of the story. And the two are connected. Typically, things which are very coherent don't like to interact with each other or the environment. That's the reason they are coherent. So it's a constant struggle. Like all of these different platforms, they balance this in different ways. A quantum system behaves like a quantum system as long as you don't look at it, right? You don't try to interact with it, but then I cannot use it. Superconducting circuit sort of falls on the other extreme. These are big systems, often millimeter in size. I'll show you some picture in the next slide. And they are very easy to manipulate because they interact very easily. And because of that reason, they also interact with things you don't want them to interact. So you have to work hard to engineer that interaction and make them long-lived. But things have come a long way. 1999, the first demonstration of a superconducting qubit, it lasted about 5 nanoseconds. That was the coherence time. Now we are approaching milliseconds. So 6 orders of magnitude, and there is really no fundamental reason why it says it cannot be more than that. There has been a steady progress in that. So as I said, there are many approaches, but currently trapped ions, superconducting qubits, photons, and then maybe, and I guess cold atoms, I would plug them here. There are some technical details which make cold atoms more suitable for doing quantum simulation type of experiments, but that also is now changing. There were some very cool demonstrations recently where they could move actually physically like atoms from one location to another locations by moving electromagnetic fields and creating interactions, and they did some very nice demonstrations, including some error correction demonstrations as well. So these are the ones you hear in the news most about is the superconducting qubit approach and the trapped ion approach. So IBM, Google are the two big names which are building some of the largest systems here. IonQ, Honeywell are some other names which you might have heard for trapped ion system. Intel is working on this along with many academic groups, of course. So now we'll discuss the superconducting qubit. And again, there are many types, and I will briefly mention that at the end of today's lecture. But the simplest one is actually nothing but an oscillator. And in fact, it's an oscillator which behaves sort of like the pendulum. Okay, it'll get clear in a little bit. And this is the circuit of a superconducting qubit. This little circular loop is what you saw in the previous picture as this circular loop. These two crosses, they represent what's called the Josephson junction. That is this little piece here. You can see there is one film of aluminum and another film of aluminum, and they are overlapping. And in between them, there is a very thin layer of oxide. So it's a tunnel junction. It's two metals separated by a thin insulating barrier. But this is a superconductor at low temperatures. So Cooper pairs have to tunnel through this barrier. And that electrically behaves like an inductance. So this is one example of such a qubit where you have two Josephson junctions in the middle. And the reason you have two here, it's not needed, is that if you put two in a loop like this, you can apply a magnetic field and actually tune the inductance, which means you can tune the energy level separation between the ground and the excited state. Because what is the qubit states here? It's just oscillations with different energy. So if the state 0 is the oscillator in its ground state with 0 quanta, and state 1 is the oscillator with the minimum amount of energy you can put in one quanta. So you can actually tune that separation electrically by applying a magnetic field to, through this loop. And of course, if you have to be really accurate, there is always half a quanta of 0-point fluctuations on top of that. But that's just for a detail. But that's what the qubit is. In compared to electronic states in an ion, like the states of the electrons in the ion, here it's a collective states where this vast Bose condensate of Cooper pairs is sloshing back and forth, and together that degree of freedom. And if you want to compare it to the classical picture, it's this angle degree of freedom, right? The pendulum has, again, infinite number of atoms in its object, but you can represent the motion of the entire pendulum if it's a rigid system with just one angle. So it's sort of a similar idea here, is that even though this object is composed of millions and millions of atoms, this collective degree of freedom behaves as a quantum mechanical degree of freedom. It can be quantized, and if it's protected from the environment, it can actually show that quantum mechanical effects. Okay. So this is, but look at the size scale, right? This is 200 microns. So this thing is almost a millimeter. And I wish I had brought one chip, but you can see this with your naked eye. But yet, at low enough temperature, under the right conditions, this shows the effects of quantum superposition and entanglement. Yeah.
All these devices that you mentioned, the trapped ion and this one and the quantum dots, they are all at low temperatures, liquid helium.
So I'll go to the next slide and then I'll answer your question. Okay. So the question is, what is that? Are all of them operating at low temperatures? So we first need to understand why the low temperature is needed in this case, and then I'll address the other problem. Okay? Yeah. That's right. So this little square here, which is basically a blow up of this part, that is this part of the circuit. And these two metal pads are just like the two plates of the capacitor. So it's like it's a parallel plate capacitor. It's not a parallel plate capacitor because a parallel plate capacitor has two plates on top of each other. But two metallic plates next to each other also have some capacitance associated with that. So we engineer this. There is a reason this pad is of a certain size. There is a reason why this junction is of a certain size, because that determines the value of the inductance and the capacitance. So here is another picture from one of IBM's papers where the same thing is now shown on a bigger chip. So now the qubits are here. So these are the two rectangular pads, and the Josephson junction is in the middle, which you cannot see in this picture. So there are two such qubits here. And then there are these little squiggly lines. These are actually microwave Fabry-Perot resonators on chip. Okay, these are transmission lines, and they help in creating the interaction between this qubit here and that qubit there. And the other one here is connected to the measurement, which I'll discuss in a couple of slides after this. Okay, I just wanted to show you another version of this. These are slightly smaller compared to this picture here. There are some technical reasons for that. Okay, so just a little bit of detail on the Josephson junction. So it's a superconductor, insulator superconductor. So here's the blow-up picture here. It's often represented as a cross or a cross with a box, where the box sort of represents the intrinsic capacitance of this structure. Because see, the tunnel junction also looks like a capacitor because it's a metal, insulated metal. But so it has some associated capacitance with it, which is sometimes represented like this. But the capacitance I drew in the previous picture was much bigger than that, and it comes from the rest of the structure, not the junction itself. That's usually the limit. And the electrical properties of this element were written down and invented by Brian Josephson, and he won the Nobel Prize for that, is that there is the current flow through this junction, which is a supercurrent, right? So this system, which even though it has an insulating barrier, actually can pass a current, which we call as a supercurrent, because it doesn't develop any voltage. It behaves like a superconducting wire. And that is proportional to this constant I0 into sine of delta. So this delta is actually what is called as the gauge invariant phase difference. It's sort of one way of thinking about it is the phase difference of the superconducting wave function defining the superconductor on this side and on this side. Because of that insulating barrier here, those two phases can take different values, and you can twist that phase by applying a current. If you connect this to the pendulum picture, this delta is nothing but the angular displacement of the pendulum. So the larger the displacement, the larger the current, but there is a maximum current you can pass through it, after which it breaks down and it no longer behaves like a superconductor. And if I is constant and less than I0, then delta is constant and delta dot is 0, and you have 0 voltage. So you have a fixed current which is smaller than the critical current. You get superconducting behavior where you have no voltage being developed, which means no dissipation. There's no resistance in it. But if you have an alternating current, you can get an alternating voltage across it. But because of this derivative, the current and the voltage are always 90 degrees out of phase. Right? This is something you learn even for an inductor, a pure inductor. So it doesn't give rise to dissipation. The net power dissipated is 0 because time integral of sine and cos over one period is 0. If you combine these two together in the right way, you get a an equation which basically tells you that the inductance is now a function of the current flowing through the system. And there is a small signal inductance, which is often called the linear inductance of the system. So if you have very tiny amount of current, then you get an inductance which is basically inversely proportional to the critical current. So it's this phi naught, which is the magnetic flux quantum, divided by 2 pi I naught. And then the overall inductance depends on I. So it's actually a non-linear inductor, right? This is again where I connect to the pendulum picture. A pendulum, even though when we study in high school, we approximate it as a linear oscillator, because for small angles, we say sine theta is theta. But if you don't do that, then it's a non-linear oscillator, and it does not have a harmonic potential, but it actually has a cosine unharmonic potential. The consequence of that for a pendulum, a classical pendulum, is that the frequency of oscillations as you make the amplitude larger goes down, because the restoring force is smaller than a linear increase. It goes as the sine of the displacement. The quantum mechanical equivalent is that the quantized energy levels of a cosine potential are not harmonic, but each subsequent level spacing becomes smaller and smaller, right? So it's a nonlinear spectrum, and it is this nonlinearity which allows you to treat this system as a two-level system, because the two lowest levels have a different resonant frequency compared to the first and the second and the second and the third. So in fact, this kind of qubit is actually a multi-level system. It has typically, depending on the design, it may have 4 or 5 levels inside this well. But we typically restrict the dynamics to the two lowest levels, and you design it in such a way by choosing the Josephson junction parameters that the difference is large enough that you can treat this as a two-level system. Sorry, was there a question? Yeah. So that's the picture. So this is the simplest superconducting qubit, which is a weakly nonlinear oscillator, created using a nonlinear inductor made out of Josephson junctions and shunted by a capacitor. It is also known popularly in the literature as the transmon qubit, because you might have heard this term. It was actually not the first qubit, superconducting qubit, to be invented. It actually is one of the last ones to be invented, but it is the most successful and popular qubit, which is used in all large-scale quantum processes which are being built today. Okay. A very important point which I have to mention, which is sort of something very fascinating about the Josephson junction, is that it's really the only known nonlinear circuit element which is also non-dissipative. These equations by themselves tell you that this system cannot lose energy. The superconductivity, of course, plays a role, but you know, this is a sort of a big deal, because the other systems where we are used to exploit nonlinearity is optics, right? Optical systems. And optical nonlinearities are hard to come by, which are strong enough, and they are almost invariably associated with some dissipative processes which are also present. So this is a purely nonlinear system, and it sort of has played a big role in making these kind of systems very, very powerful. Okay. So now let's look at some numbers. So I have put some values of inductances and capacitance. So these are typical numbers for this system. You have these energy levels there, and we operate at a temperature. So Spenta, I'll come back to your question after this, such that the thermal energy is much less than h bar omega r. What is omega r? It's just the simple LC resonant frequency, or it's the frequency of the energy difference between the first two levels. You want to ensure that this thermal energy is much smaller than the energy level spacing, because you would like your quantum system to be in a well-defined pure state. Here, thermal energy can just create a Boltzmann-like distribution across all the levels, and that is not a very useful state to work with for quantum systems, right? And if you put in the numbers for these values, that resonant frequency is around 5 gigahertz. You turn that into a temperature by basically doing h bar omega over k Boltzmann, that is about 250 millikelvin. And the typical experiments are done at a temperature of 10 millikelvin, so that this is nicely satisfied. All this time I kept telling you it's just an oscillator, it's just an oscillator. This is the reason why the oscillators you experimented with in your undergraduate lab cannot show quantized energy levels. They are typically in kilohertz, which means 6 orders of magnitude lower energy than this, and you're typically operating at 300 Kelvin, which is several orders of magnitude. So you're like gone completely in the other direction. Thermal energy is orders of magnitude higher than the energy spacing between the quantized energy levels of your system. Right? So you have to be in the right regime to be able to see the quantization effect of such a system. And that's why the temperature is important. And this is often, a question which people ask is that, we use aluminum as the superconductor. Typically, it becomes superconducting at 1 Kelvin. One of the reasons you also want superconducting elements is that the analog of decoherence in the oscillator model is just dissipation. That's one of the simplest things, right? You start a pendulum to oscillate, it stops after some point of time. That is exactly equivalent to you put your quantum oscillator in the excited state, it went back into the ground state. Where is it dissipating that energy? Into the environment. What is the environment? It's the resistance of these circuits. So if this capacitor was not a pure capacitor but had some resistance, which is true for any capacitor inductor we make for operating in our regular electronics, that energy will get dissipated in no time. So the superconducting aspect helps you to make circuit elements which have very small amount of dissipation, and you need to go even lower in temperature just because of this scales involved. So another associated question is that, okay, and this is often connected with the idea that people view going to 10 millikelvin as a very hard thing to do, right? It depends on how you define hard. It's a very expensive piece of equipment. It's about $500,000 to make, but it's a 50-year-old technology. It's off the shelf. You can buy it. So often the question asked is that, well, why don't we make it 50 gigahertz? Then I can operate at 10 times more or temperature or 100 times more temperature, and then I don't have to buy an expensive refrigerator. Maybe I can buy a cheaper refrigerator. The problem is that 5 gigahertz is actually very convenient for other reasons. A lot of IT and telecom technology has perfected this frequency range. 50 and 100 gigahertz now starts approaching this terahertz kind of region, and there are no good sources over there. Then you have to go to optical frequencies, where actually also lasers are not so easy to use as microwave sources are. But now you are not talking about a completely different regime. That's where you use things like atoms and stuff like that, right? Superconductors have an energy gap. That energy gap tells you the scale where you can operate. So you can say, well, you can use high TC superconductors. It's not so easy to make high quality capacitors and Josephson junctions which are dissipation free. So there is a reason why this sweet spot exists, even though now experiments have started to push this a little bit higher as we understand and control this better. But this is a very sweet spot, and in fact, from an experimentalist point of view, it had a huge role to play in how quickly the superconducting qubit community was able to run through all the experiments which the quantum optics people did with a lot of difficulty over decades in less than a decade. Because the instrumentation and the hardware was so good, and it was off the shelf, cheap, and very easy to use that we could just go through. Because it's the same physics, just in a different setup, they were able to run through the quantum optics experiments and also do new quantum optics experiments in regimes which were impossible to imagine in the optical case. Because I can control my inductors, my capacitors, I can control the interaction strengths. So this is actually quite nice that it worked out this way, and going to the 10 millikelvin is just some money at this point of time. Well, there are challenges also. You cannot make them very big, but people are trying. Okay? So as I said, low dissipation, no friction superconductors, and because of this reason, you can expect that if I just leave the system alone, it will end up in the quantum ground state. And this is very important for quantum information processing, is that you need to know where you're starting to know where you will ultimately end up. If your initial state is not a known pure state, you cannot do quantum computing, right? Now, just a side caveat here, I've said that this is the case. Sorry, how much time do I have? The thing has died. Okay, about 20 minutes, right? That even though we do satisfy this, in reality, we actually don't find it in the quantum ground state, because of some non-equilibrium effects, and we have to do something else to actually ensure. This is in the quantum computing lingo, it's called initialization of your quantum states, and that's also important. I'll hint at that later on. Okay, so.
Can you explain the last thing you said? What goes wrong?
Which one?
I mean, you said that this is difficult to achieve. This initialization.
This is not, I'm saying that it's not difficult to achieve, it's just that the system, even though the thermal temperature is low enough, there are some non-equilibrium processes which give rise to an effective temperature. So these are, for example, these could be due to energetic photons from both within the cryogenic environment and from outside, which impinge upon your superconductor and break Cooper pairs. And that sort of creates these excitations. So those do tend to happen. We try to do something with the circuitry, you'll see a little bit later, to minimize those, but they tend to happen. So I'll give away the answer. The way you actually initialize is actually using measurement. If your measurement is able to localize the two states better than the system is localizing by itself, you can use the result of the measurement to know what the initial state is. So there are two ways there also. You can measure. You will find most of the time that you are in the ground state because there's this non-equilibrium excitation is usually small, of the order of a few percent. And you can just ignore all experiments where you found it in the excited state. So that's just like losing some statistics overall. But if you had fast electronics, you can actually apply a pulse to bring the system back to the ground state. So then you start with 100% ground state, 100% to the accuracy with which your measurement can determine, which is actually the next slide. So you will see how good those things are. So you now have your nonlinear oscillator here in blue, which is your quantum 2-level system. I now need a way to measure it, right? I will come back to how you actually make the states after this, but I already mentioned this, that you have to use microwave frequency, which is resonant with the 0-1 transition. That's the way to manipulate the state. So in order to do the measurement, what you do is you actually couple this nonlinear oscillator to a linear oscillator, which is off resonant from the system. Okay, see, this looks like a coupled oscillator problem, and it is, but they're off resonant, and it's actually this kind of interaction is represented by the Jaynes-Cumming Hamiltonian, where typically you approximate this nonlinear oscillator as a 2-level system coupled to a harmonic oscillator. But in this detuned regime, where there's a coupling strength G, which tells you the interaction between the nonlinear and the linear oscillator, and there is a coupling to the environment kappa, which is the rate at which this cavity decays its information to the environment. Now the environment has come in because we want to measure the system. Some information has to be extracted. So in this regime, which is called as the dispersive limit of the Jaynes-Cumming Hamiltonian, what you end up getting is that the resonant frequency of this linear cavity is modified by the quantum state of this qubit, which means that if I look at this cavity from the environment and try to look at its resonance, I will see two different values sort of shown here, corresponding to whether the qubit is in the ground state or the qubit is in the excited state. So this is a resonance curve plotted in the terms of a signal which is going in and reflecting back, and you're looking at the phase. Typically, you might be used to seeing resonance curves as a peak or a dip. Here, in this idealized model, there is no power absorption going on because all of these components cannot absorb energy. That's actually very important here, right? So there is no information in the amplitude of the signal which is scattered from the oscillator. All the information is in the phase. So you get this 2 pi phase shift as you go through the resonance, as you sweep the frequency, and then you get two different shifted values depending on whether the system is in the ground state or the excited state. And the way you measure is you of course characterize this, and then you choose a frequency right in the middle, and you look at the phase shift. So if it was in the ground state, you will get a phase corresponding to this value. If it was in the excited state, you'll get a phase which is corresponding to this value. So just from the point of view of signal processing, all you're measuring is a sinusoidal signal whose phase is shifting between two values. And that tells you whether the system is in the ground state or the excited state, right? So the cavity frequency now depends on the qubit state, and qubit state measurements are essentially implemented by sending a microwave pulse and measuring its phase shift, right? That's all. So this is now sort of the basic building block of your any system. You have your qubit, which can be controlled with microwave pulses. You have your measurement apparatus, which is controlled also, probed also using microwave pulses. Okay. And here is an example of such a measurement. Okay. So let me just take a minute to explain what's plotted here. The x-axis, you can think of that as the phase shift. It's actually voltage, but its voltage is proportional to the phase shift. And the y-axis is the probability of getting that phase shift value. Remember, these are real experiments. If I'm trying to measure a phase shift of 35 degrees, I'm not going to get 35 degrees. I'll get a distribution around 35 degrees. So what you're actually seeing are histograms. So the red and the blue correspond to the ground and the excited state histograms. And you see that when the system is in the ground state, the histogram is peaked mostly in this region. And when the system is in the excited state, the histogram is mostly peaked in this region. Note that the y-axis is a log axis. So from here to here, there is nearly 3 orders of magnitude, or at least 2.5 orders of magnitude difference. What this means is that if I had plotted this in a linear scale, these are two Gaussians, which are very nicely separated with very little overlap. The overlap comes from this region, right? That tells you the error you're going to make in knowing the state of the system. There is a very small chance, just because of fluctuations in your signal, that you will incorrectly identify your state. Ideally, what you want a very clear signal for the 0 and a very clear signal for the 1, and there is no like overlap between them, but experiments have realities. But apart from that, you also see these smaller bumps. See, you see a red colored bump underneath the blue colored bump, and a smaller blue colored bump underneath the red colored bump. This is not due to noise in the signal. This is due to the fact, so the bump of the blue on the red side is easy to understand because the measurement of this phase also requires a finite amount of time. Your qubit could decay during that time from the excited state to the ground state. So some counts will end up here. It's a small number of counts, but it's still finite. Right? So here again, the coherence time plays a role. If you are not able to measure this fast enough, your system will undergo a change and you will end up measuring something incorrectly. But you also see the opposite, that the ground state is showing a bump on the excited state signal side. This also happens. This can happen due to this non-equilibrium process I just mentioned a little before. But this can also happen because of the act of the measurement itself. Not in a fundamental sense of a textbook quantum measurement, but a more practical sense that in this Hamiltonian, even though this process should not be possible, when you include the higher order terms, these processes become possible. This actually is a very important technological problem which is currently being solved. Even though, look at this number, 98.86, this is actually data from one of our experiments here. This basically is telling me that I have a 1-point-something% chance of incorrectly identifying my states, either 0 or 1. The state of the art for these numbers is a little over 99%, but we would like this to be 99.99 or maybe even 9. Because you cannot, as you're trying to do more and more complicated algorithms, you cannot even make error in the identification of the answer, particularly when you want to do error correction, because error correction is based on the result of the measurements. So even if you make a mistake 1 in 10 to the 5 times, it's not so great. So you would like to push this. So there's a lot of work, including in our lab, where we're trying to understand, and there's actually a lot of theoretical work needed here to understand the dynamics of this type of a system, like why it causes these transitions to happen, even though the lowest order Hamiltonian says that those processes should not be possible. It's actually a simple energy conserving argument. These two are non-resonant. I'm putting photons at this frequency, they should not cause any state transitions in this subspace, but they do because of presence of higher order terms. So this is sort of tells you how good these are. And remember that if this was 99%, then I could, and my thermal non-equilibrium population was 5%, by measuring, I project the system and classify the states in a much better way than just leaving it alone. So this is why you can actually do this. And a lot of experiments start, it's very strange, the experiment starts with the measurement. And then the rest happens. You sort of initialize with a measurement, but there are other techniques also which use the fact that there are higher levels. You can use various Raman processes and things like that, which will create an effective path to the ground state and make it highly likely. So these are called cooling pulses, and you can also use that. It's not so easy to do it in a transmon qubit, but there are other qubits where you can do that. Okay. Now, with this kind of ability, you can also see these kind of signals, where what I'm showing is 6 different traces where the experiment was started out in the excited state here, and then we just kept observing. So the y-axis is now like is the phase shift, and you see the qubit actually decay in real time from the excited state to the ground state in this jump-like fashion. This is nothing but what is called as quantum jumps. Right? So I was lucky to be part of the experiment which did it the first time on superconducting qubits back during my postdoctoral days at Berkeley. And now this data is of course from our lab here at the TIFR. This is a very routine thing we do now. And this uses some very low noise superconducting qubit junction based amplifiers called the parametric amplifiers, which I won't really have time to discuss. Okay, so maybe I'll take 5 more minutes and then pause for questions, right? So now coming to the controlling aspect. So I already mentioned that you need to send microwave signals which are resonant with this transition, right? You need to send some electromagnetic energy. So if you now take a pulse at omega 01 with a finite amplitude and time, and then you sweep the time, you actually get something like this, and then you measure, right? You actually get that so what's plotted on the y-axis is the probability of being found in the excited state. That is again determined by the phase shift measurement. And then you get these oscillations. It goes to the excited state, back to the ground state, or to the excited state, but is also decaying. The reason it's decaying is because of decoherence. This phenomena is called Rabi oscillations. This is a well-known 2-level driven system. One of the first time-dependent perturbation theory calculations we often learn in intro quantum mechanics classes is this thing, and that's the essence of controlling a qubit. Okay, the amplitude of this drive determines the frequency of these oscillations. So harder you drive, faster it changes. Okay, these are important from the technical point of view when you're trying to do this. Okay, then the phase of this signal, which means with respect to some arbitrary time starting point, is it a sine omega t or a cosine omega t or something in between, that determines the axis of rotation, right? There is no absolute axis. You can always choose some reference point, but with respect to that, so what this means is that am I rotating from 1 to 0 like this, or am I rotating from 1 to 0 like that? Why is this important? Because it creates different superposition states pointing at different angles depending on where you stop. So this is another degree of freedom we have control to position the quantum state on this Bloch sphere. And finally, the amount of time you have this pulse on determines the amount of rotation. So if I wait long enough for it to come all the way down to the 0 state, that is called a pi pulse. It gives you a full 180-degree rotation on the Bloch sphere. If I do only half of that, I get something called the pi by 2 pulse. That is what is used to create equal superposition states, right? So now the job from an experimentalist point of view to implement these local single qubit operation is just to figure out what is the correct amplitude shape given to this. There are some other details like should it be a square top like this, should it be a Gaussian envelope, those all have other implications on this, but essentially that's the idea, and then you can now create any superposition state by playing around with these numbers. Okay. So single qubit gates are essentially then done using that. So you can now apply a pi pulse, and that becomes the NOT operation because it will take 0 to 1 and will take 1 to 0. You can do the Hadamard, which will take 0 to 0 plus 1 or 1 to 0 minus 1. You know, these are rotations about an axis which is x plus z over root 2. And then all of these single qubit gates are nothing but rotations on this Bloch sphere. You start somewhere, you end up somewhere else. And a microwave pulse of the right type allows you to do that. And that's essentially how you do single qubit gates. Okay. Now coming to multi-qubit gates, I mentioned already that you need some interaction, and this is sort of just a very simple calculation to show you why you need that. Right? So now let's imagine I have 2 qubits, and I've just shown you how to create any arbitrary superposition of either of these qubits. Now, if you take both of these qubits combined and write them together in this joint form, which is often called the product state, and you now look at the coefficients here and you say that, can I create a state like this by just finding the right value of alpha 1, alpha 2, beta 1, and beta 2, because that's what I can control here. And you'll quickly see that it's not possible, because here I need the coefficient of the 0, 1 term to be 0, so I can make alpha 1 0, but if I make alpha 1 0, this also becomes 0. If I make beta 2 0, then this also becomes 0. So you realize that this state is impossible to represent by alpha 1, beta 1, alpha 2, and beta 2, because this is what is called the entangled state. And now I'm sort of, you all know this, I'm presenting it from an experimental perspective, that by just messing around with alpha 1 and beta 1 and alpha 2 and beta 2 independently, I cannot create this state. I need to do something else, which comes from the interaction. Okay, so you cannot create entangled gate states by single qubit gates only. You need something which depends on both the qubits. Okay, so here is a truth table of something called a control NOT gate. So C and T represent to control and target. This is just a nomenclature given to the 2 qubits participating in this gate. Control means is the one which you are setting the condition. Target means the one which is changing because of that condition. Okay, and the truth table says that if both control and target are 0, 0, then they remain 0, 0. If it is 0, 1, it remains 0, 1. If it is 1, 0, it becomes 1, 1, which means that if the control is in 1, it flips the target from 0 to 1. And the same way, if it is 1, 1, it shifts the target from 1 to 0. So the controlled NOT operation tells you that if the control qubit is in state 0, it does nothing to the target. And if the control qubit is in state 1, it applies a NOT operation to the target. Okay. Now, why is this useful? First thing to remember is that here the operation on the target depends on the state of the control. And if I now take the control in a superposition state alpha 0 plus eta 1 and the target in 0, so the product state is gamma 0, 0 plus eta 1, 0 written with control first and target later. And if I apply this control NOT, you will see that the 0, 0 component will not change, but the 1 component will flip the target and you will get eta 1, 1. This is now that state which you were trying to create. So a truth table like this, if you can implement, I have not shown you how to do that in the actual experiment, but this is what you need. And the essential idea is qubits have to interact with each other, and the basic principle is that you have to engineer the physics of that system in such a way that the target's evolution depends on the state of the control. And then everything just extends. When you create superposition states, then you just have to operate on each component of the superposition according to the rules, and the final state will be based on that. Okay? And this is typically done by creating physical interactions. Remember, these are 2 electrical oscillators. How do I make them interact? I can just put a capacitor between them. Here, interaction literally just means that any oscillating signal on this guy should have some implication on the other guy. That's all it means. That's all interaction means here. Some electromagnetic interaction. I can put a capacitor, but this capacitor can actually be other electrical elements as well. I already showed you one picture before where instead of this capacitor, it was this section of a transmission line. Okay? So it's sort of like an extended capacitor so that I can send signals across a larger distance. Because this is a microwave transmission line, it can transmit signal from here to there. Why this is important is because if I only could use capacitors, capacitors are essentially done by putting things next to each other. It becomes very difficult to pack many, many qubits. But because of this, I can now keep the qubits far apart and have these connecting transmission lines between them, and that gives you a practical way of putting them. That's a very good question. That's the next one. So when you make capacitors of this type, these are called architectures with fixed coupling. So they are fixed by design. But you can, if you could design a circuit which is a variable capacitor, which you can, but mostly what you do is that you actually create a circuit here. So let me just orient you here. This qubit looks very strange, but this plus here is one of the plates of the capacitor. And the other plate of the capacitor is all the ground plane, and the Josephson junction is somewhere here. So that's one qubit, and that's another qubit. So again, same LC oscillator, just a different shaped. And in between, there is a circuit which is composed of these Josephson junctions, but with these loops. So here what you do is you put a magnetic field through that, which sort of changes the inductance in such a way that you can now control the electromagnetic interaction between them. There is not a very simple way to create a variable capacitor using superconducting circuit elements, which is again dissipation free and things like that. So the tunable elements we have at our disposal in our toolkit is Josephson junctions in loops. Now, new stuff is coming up using 2D materials. So like you can make Josephson junctions using graphene, where you can now apply a voltage instead of a current to create a magnetic field. But the technologies are not entirely compatible, so it's not so easy to make them at large scale, but these kind of experiments have been done, and that may have some implications to be able to create easier versions of this capacitor. But essentially what you're saying is correct. Any electrical circuit whose properties can be tuned by a signal can be used to turn this interaction on and off, and this is actually an important aspect in the construction of the quantum processor as well. While several successful processes exist with this fixed coupling, you cannot turn the interaction off, and that's not ideal. In the most ideal quantum processor, you would like all the qubits to be isolated and interacting only when you like them and only those which you want them. So a tunable coupler architecture is probably the way to go. Just that in what has happened internationally is, like the two big companies, IBM started with the fixed coupler, and you can see the the attraction of a fixed coupler is that once it's done by design, it's there. Whereas a tunable coupler requires an extra wire to control that as well. So it's more expensive from the resource side. And also when you bring in an extra wire, you can also bring in noise along with it. Right? So initially people were a little skeptical, but this is just an engineering problem. So this has now been mostly resolved. Though typically people do see that architectures with fixed couplers have higher coherence times than compared to architectures with tunable couplers. But these interactions which can never be turned off actually give rise to some errors, which are always, so it's like your qubits are evolving in a deterministic way, but not in the way you want. It's some background evolution which is constantly going on. There are some techniques to constantly fix it, but it's a pain. So even, I think now IBM is moving away from this. Their latest processor, which has this 133 qubits, uses tunable couplers. But you pay the price of extra overhead, because which means that you needed one line for controlling each qubit. You needed one line for measuring each qubit, though that measurement part can be multiplexed and you can share a common line amongst multiple qubits. But now you need an additional line for every connection between the qubits, right? So it actually is not just scaling linearly with the qubit, it's going as some small polynomial, because for every other qubit, there are several connections. So, we had to, so one has to worry about that. But are the two basic approaches, fixed coupler architecture and tunable coupler architecture. Yeah.
So the coupling between them is, you said a microwave channel?
Yeah.
So that's like a coax cable basically that carries a microwave photon, or?
This is a on-chip coax cable. You can think of it like
So it carries microwave photons?
Yes.
And basically it would be like one photon would
So this is a little bit more tricky. So depending on the kind of interaction you're using, there may be no real photons in them. It could be entirely a virtual excitation, right? And the reason for that is that this piece of transmission line, which has sort of two boundary conditions, can be thought of as a microwave resonator because it has two boundary conditions. the resonant frequency of that resonator and the resonance frequency of the two nonlinear oscillators, they're all different. So they cannot create excitations, though there are architectures where what you do is that you swap this photon in this qubit onto this resonator and then from the resonator back onto this. But that typically is, it's one of the choices, but it's not typically done, because then if this transmission line is not like completely lossless, then the photon can decay while it is in there. So by using virtual excitations, you are able to actually use this without worrying about the losses in this section so much. So typically that's the approach that is used. But the tunable coupler ones typically create resonant interactions where the different qubits are brought to create interactions. So one very simple way is to have two qubits which are exactly the same frequency, and then they are disconnected, and then the coupler turns on, and now they are actually on resonance. So what happens when two coupled oscillators are on resonance? You have this energy swap back and forth. That is a 2-qubit quantum gate if you stop it at the right time. So there are many approaches. The fixed coupler architectures typically use off-resonant interactions, which are sort of present in the background, and then you add an additional field which actually enhances that rate to what you want. And that's how the gates are turned on and off. But this background interaction always remains, and it's given the name coherent errors. And this is something you have to fight in this architecture. Okay. So all of this essentially gives you this idea that you can make the state of the evolution of one qubit dependent on the state of the other, and that's the essence of the entangling gate. So maybe this is a good time to stop. I just had a couple more slides, but yeah, we can continue that. So yeah, so I will stop here and take any more questions there are.
Questions?
So you have these qubits, each of which is this set of two Josephson junctions.
Or one, actually, yeah. There could be also one.
Or one, I see. Okay,
So
you had two.
So you need, if you want them to be tunable, you need two, otherwise you just use one.
Okay. So you have these Josephson junctions, and then just to get a sense of what a quantum computer would look like, and then you have some huge dilution fridge or something going down to whatever, 10 millikelvin. Okay, right. That's the picture, I see. And then all the qubits hang at the bottom.
Yes.
And all your wires go down, controlling the qubits and reading out. And
that's right.
Okay.
So at the end of the day, it's a chip in an enclosure with lots of microwave cables going in and out. And the algorithm runs by just bouncing these microwave pulses of the right shape. The shapes of these pulses determine the operation they are doing. And then at the end, you send another set of microwave pulses to detect the state of the qubit. So that's sort of the overall operation. That's sort of the last couple of slides, but I'll go into that in the next lecture and then move on. But, yeah.
Any other questions? Okay, if there are no more questions, let's thank Vijay again for giving us a very nice overview.